tells you that there's some new object been deleted or added to that device. In other words, there's semantic characteristics of the device have changed. And so you have to be careful of that. If you're a client, you want to refresh your object list from the device to get the latest version of how that device is configured. The parameter revision tells you if in fact somebody has gone in and changed a setting. So that if there's a setting change in the device, for instance, the trigger points on an instantaneous overcurrent protection block have changed, the parameter revision will increment. That tells you there's a new value in here. So this tells you that there's something different in that device. If your application cares about that, you can detect those kind of changes. And with the value revision, this tells you if anything has changed in the configuration fields. So if we go back into, like, for instance, the CF, these are the configuration fields. So if somebody goes to an object and changes the control model from select before operate to direct operate, what will happen then is you'll see that change in the value revision. Here's a common data class definition of a measured value. You'll see an interesting thing here is you have two values. One's an instantaneous magnitude and a magnitude. And one has a trigger option of data change, where this one doesn't. What this is telling you is that a magnitude value can trigger a report, a data change. Where if you put an instantaneous magnitude into a data set and it changes, it will not trigger a report. So by very carefully selecting the data that goes into data sets for reporting, you can have very good control over how devices report data. So here you can see we have these instantaneous and the magnitude. We have range alarms that tell you high, low, high, low, low, etc. Quality and timestamp. Substituted values, what the units are, if there's a deadband associated with the magnitude value, what that deadband is, what's the range, the sample rate, etc. All this information is potentially available to you from the device. So the difference between an instantaneous magnitude and a magnitude value is that some deadband's been applied to it. Now 61850 doesn't define this particular algorithm as in every device, but this is representative of the kinds of deadband algorithms that devices implement. So that on the magnitude value, you get discrete changes between steps as the voltage changes, where an instantaneous magnitude, you get a reading at whatever point in time that value is read. Sampled values is what's used for instance, synchrophaser communications. And in a sampled value, you only have an instantaneous. There is no deadband applied in a sampled value. So here you just have instantmag only, and a quality and a timestamp, of course. And you'll see that you don't get data changes if you put that value in a report. And that's why in process bus, as we'll see shortly, that's the communications of sampled values handled a little bit differently than they are for measured values. So here's the common data class for Y-connected measurements, phase to ground measurements, phase ABC designations. They're complex measured values. You have you have angle references that are represented here, which could be based on synchrophasers. Excuse me. A complex measured value consists of a vector, not just a magnitude, but a magnitude and an angle. And that's the difference between the measured value and a complex measured value, essentially. And again, the angle reference can be voltage, current, other, or synchrophasers. So these changes that are necessary to represent synchrophaser information have already been incorporated into 61850. But you'll see here there's a lot of the sample rates, the range values, the range alarms, etc. are all available with the complex values as well. So with logical nodes, I'm going to go through this very quickly here. There's a whole bunch of slides here, and there's the names and designation of each one of these things. You'll see that all of these ones on these pages, there's a naming convention associated with these devices. Thank you. So that the system logical nodes, these are things that define the device itself, the system. They're all defined with an L. You've got automatic control, which includes like tap changers, voltage control, alarm handling, cooling groups are in this C for the supervisory control. Functional blocks for, generic filters, ramps, PID regulators, etc. You've got generic automatic process control, generic logs, generic I/O. Basically, you should only use those when there are no power system functions available for representation using another logical node. Interfacing and archiving, beginning with an I. You've got mechanical and non-electrical type things like filters and pumps and tanks. Metering and measurement logical nodes, harmonics, measurements. You've got sequence and balance, statistics, hydrological information, DC, etc. Many protection functions. Instantaneous over current, differential direction. We're not going to list all these things here, but just to give you a general idea of the scope of the standard and how much of it, of the power system functions that exist in the system, now there's a standard that defines how these things work. Power quality events, protection related things like reclosers, differential measurements, disturbance recorders, sensors and monitoring for looking at arcs and insulation. Instrument transformers for not just current and voltage, but frequency, generic sensors, etc. Switchgear, circuit breaker, circuit switch, power transformers, other stuff like batteries, capacitor banks, resistors, etc. So it's a very comprehensive model. Then there's detailed logical node definitions for each one of these objects. The logical node names you'll see from these diagrams up here, we've got these 4-character names, and the way you construct the name in a device is you start with the 4-character designation. In this case, this is for a circuit breaker. XCBR is the 4-character designation for a circuit breaker. You can have one or more circuit breakers in a device, and you can have a prefix that's application specific. And later when we talk about SCL, we'll talk about how these prefixes get generated. But this is the name of the circuit breaker. So anytime you see an object for which there's an XCBR in the name, it tells you that's a circuit breaker object. Now the rule is that there's a limitation that for addition 2, the prefix digits and the instance digits have to be less than or equal to 12 characters. So we have, for instance, a logical node that's a description of the physical device. And here you've got the physical nameplate associated with the device and the device health. So you have the nameplate and the health of the device. This is information about the physical device itself. Plus, there's a bit here that tells you if it's a proxy. So if the information within that logical device is being derived from some external device, the proxy bit is set, and in other logical nodes, you can access the external equipment information associated with where those measurements and status values come from. There's a common logical node, and I put this up there simply to show that every logical node has these common functions in it. So every single logical node has mode, behavior, health, and a nameplate associated with it. So every power system function that's defined in 61850 has these parameters associated with it. You have a common logical node that defines the status for it's like a global logical node for the entire logical device. So you get mode, behavior, and health for the logical device itself. And then you have individual logical nodes that describe the information associated with those specific power system functions. In this case here, we're looking at the circuit breaker logical node. In a circuit breaker logical node, you've got a local remote key switch that tells you whether it's in the local mode or the remote mode, whether switching authority is enabled at the local station level. You have the local control behavior, what the external equipment health is, if there's external equipment associated with that. You've got position controls, position, whether it's blocked open, blocked closed, etc. These are all organized, as we talked about before, the common data classes. So what we're going to do now is we're going to say, well, what if I want to know what the object name is of this object here, the LOC, the local control mode of this circuit breaker? So what I need is this definition here to tell me the attribute name and then the single point status which is here, where we saw for an SPS, the single point status is called status value, and it's in the ST functional constraint. So the object name is XCBR status local status value. Now, with a little bit of training and a little bit of knowledge of what these logical node names are and a few of the attribute names, it becomes very easy to understand and see inherently see the power system context. So when you want to read the local remote status from a device, that's the name. You don't have to know how it's stored in the device. The device understands this name as how that information is portrayed. A little slip of the tongue there. Now, when you look over the wire, we have to map that abstract name into a protocol, and that's what happens in Part 8.1 of the standard, where it maps it to MMS. And in MMS, you can't put periods. You can only have $signs and underscores. And so there's a process by which you convert that abstract name into a concrete name. And so if you look on the wire in an analyzer, that's the name that you'll see going over the wire. I'm going to show things with a period just simply because they're a little easier to see during the presentation. So likewise, if I want the position of that circuit breaker, it's very similar. All that happens here is the attribute name changes from local to position, POS. So if we look at the measurement unit, here we have the measurement unit block, which again has external equipment health, if in fact it's a proxy for instance, you're getting as measurements from this is an RTU where you're getting measurements from some other device that you're communicating with. We're going to look at the phase to ground voltage, which is connected via Y. And here it's a little bit more complex because we're dealing with a complex measured value, but we have the measurement units, the MX for measurement, functional constraint, phase to ground voltage, phase A, current value, angle, floating point. So that's the phase A to ground angle measurement. That's the angle for the phase A voltage. So from a synchrophaser perspective, that's the kind of tag name that you'll see, and it tells you precisely that it's from measurement unit 1. And then additionally, with the additional information I don't show here, where you get logical device names associated with it, you end up with an object name that has a lot of meaning from a power system context, and it's standardized, and it's the exact same name that the device understands. So I think I'm doing pretty good. Abstract communication service interface. So we kind of saw how the models work. So now we're going to look at how the services work. How do you access the data in these models? And ACSI stands for Abstract Communication Service Interface, and it's a way of abstractly looking at a device and saying how things like reports and controls and polling functions work, and providing a model for how clients interact with servers. So we start with a set of objects, a set of services to manipulate those objects, and some types for describing these objects. And I'm not going to go into too much detail about all the types and such, but just to give a brief overview of what some of these objects are, you have definitions of the servers, logical devices, logical nodes, etc. Report control blocks, setting control blocks. The concept of a control block is pervasive in 61850, where anytime a client wants to access a function within the device, its interaction is with a control block. So when a client makes a connection to the device and it wants reports, it goes to a report control block to tell the server how you want reports. It goes to a report control block to control Goose and to control other processes as well. The services are abstract here in this column, like get logical device directory, get dataset directory, create dataset, delete dataset. These things get mapped into a set of MMS services, and I'm just kind of showing here in green that some of these services that exist are discovery services that allow a client to make a request to the device and get a list of the logical devices that exist. And once you have the logical device name, you can get a list of the logical nodes that are in that device, and so on. This is how discovery works with 61850, and it's one of the unique things about it. And one of the reasons why MMS was chosen was because the protocol already existed and it had the services necessary to achieve those functions. So it became a natural fit to say, well, why create a whole new protocol? We've got a protocol already that exists that provides all the functions that we need to satisfy our abstract services. Reporting is really a very nice model for reporting that allows the client to interact with the device through a report control block to tell the server how you want data to be reported to you. So you can have control over the integrity period, the buffer times. In other words, how fast will reports be sent to you? Do you want data change reports or just quality change? Do you want do you want to include the names of all the objects in the report, or just send me the data values? All of this information and control over the reports can be done by the client interacting with a report control block. And you have two types. You have a buffered and an unbuffered, to where the unbuffered report says if you lose communications to the device, you don't really care if you've lost data. But if you care about it, for instance, you're looking at breaker states and things of that nature versus just simply a measurement for a trend chart, you might say, I need a buffered report, in which case the device, when it loses connections to the client, will start buffering up that information so that the client, when it reconnects, gets all the reports that it would have gotten had it been connected. And there's also a concept called logging, which is very similar to reporting, but where instead of the data just being sent to the client, it gets stored locally on the server, and then the client can come in there later and query the log and get the individual records via a read type of interaction with the device. I will say that reporting is much more commonly used. So we talked before about magnitude and instantaneous magnitude, and this is where using the data model to control reporting becomes very important. For instance, and this is an actual use case from a utility in Australia that built RTUs using this use case, was they wanted to get average current readings on all three phases every 10 minutes, along with one actual voltage measurement every 10 minutes. But if there were any under or over voltages during that time period, they want an immediate report. And so what this means is we're going to use the statistical metering function for average current measurements. We'll use the MMXU for the actual voltage measurement and the range alarms. Now when we put this in a report, we're going to use those instantaneous magnitudes, not the magnitudes. That way there's no deadband applied and they will not trigger a data change. So the only thing that will trigger a data change is the range alarms. So this is a very nice way to illustrate the power of 61850 that gives the client the ability to control how the device responds to reporting. There's a control model that allows this is the general model here, where an operator would issue a operate command to the device, to the control object. Sorry. And so he operates, he sends this command to the device. The device responds and says, I will attempt the operate. It then goes out to the control state machine. At some point later, you get a report back that's true. So that's one of the things to know about 61850 controls, is when you get the response from the device to the control request, the device is just telling you that he will attempt that control. It doesn't tell you the control sequence is complete. So there's simple direct control with just normal security. There's only a single operation where the operator sends an operate request to the device. You get an operate response positive back from the device, and it says, okay, yep, I'll let you do that. And sometime later, if you're monitoring the state, you'll get a report that tells you that the state changed. But there's also an enhanced security model, which allows the client to first do a select, where the device will tell you, yes, it's okay, I will let you select it. Then it goes and it does the select function, at which point, if you're looking at there's a status bit that tells you if it's selected or not. You could see that change state. Then you can issue an operate, which the device will tell you, I will attempt to operate, activates the output, does whatever it has to do in the control function, and then you can monitor the progress of the object changing state. And when the whole process is done and completed and the output is deactivated, you get a separate message back from the device saying the command's been terminated. So you get an absolute verification of the completion of the control operation from the device via a separate message from the device. And that's called SBO control with enhanced security. Another service is Goose. Goose messaging allows devices to share the information very fast. Here we have publishing and subscribing devices. The applications subscribe by listening for messages that are sent to a multicast destination address. Perhaps a little counterintuitive. You don't listen for where they come from. You listen to where the messages are sent to. So in this particular case here, if you've got a relay or a PMU generating a Goose message, it gets delivered to all the applications that want that piece of information, that listen for where this message is sent to. And essentially, Goose is called Generic Object-Oriented Substation Event, and it sends data set information. Essentially, you collect points of data into a data set, and that data set gets sent every time the data changes. What's in a message? You get a reference to the control block that controls the message. You get a timer that tells you how long to wait before you get this message again. So this is where we add reliability to Goose messaging, to where we can tell if we've missed any messages, because now we're going to get this message within the next milliseconds, and we don't get that message, we know that something's happened to the communication channel between us and that device. We get a state number and a sequence number, and I'll show you this in a little bit. The revision, the configuration revision, tells you if the organization of the data that's being transmitted changed, how many entries there are, and then the data. We take that data, put it in a binary packet, and send it out over Ethernet. Now, Goose is reliable because what we're going to do is we're going to retransmit the same state information multiple times and designate that with a new sequence number each time we send it. So when a fault occurs in a substation, what you'll see is a device will start transmitting state information, in this case state 1, sequence 0, very fast. You'll get sequence 1, sequence 2, sequence 3, and the time allowed to live of each message stretches out over time and increases until you eventually get to a steady state of about once a minute. So at a minimum of once a minute, you know whether you have a communication path with the device, because you can see that sequence number increasing constantly. But when the data changes, and it's critical you get an update, you get the data sent very, very fast here, because if you miss the first packet, it's going to send you another one very quickly here to make sure that you get that packet as quickly as possible. Because again, this is multicast, so there's no guaranteed transport underneath here. We're sending this directly to Ethernet. We want to make sure those packets get through, or that if they don't get through, you know they're not coming through, so that you can make control decisions. Now, sample value messages are a little different. In sample value, we're not sending event information, we're sending a stream of samples. So basically, we're taking up a bunch of samples, putting them into a single message and sending them out, and just waiting until we get that again, send them out, and just keep sending that stream of data over and over and over again. And that's fundamentally how the synchrophaser communications will work. It's going to use the sample values over an IP multicast network. And this is the kind of information that gets sent over the sampled values, where you get the control block designation that controls the transmission. You get the name of the data set, how many samples are in the message, what's the time of the first sample, what's the sample rate, whether the samples are time synchronized or not, what's the sample mode, whether it's samples per period, samples per second, seconds per sample, whether it's simulated and then a bunch of samples, and then it's the information that gets sent repeatedly to get its equivalent of synchrophaser communications, for instance. So Goose is event-driven. Sample value messaging is more stream-oriented. So the last concept to discuss here is the substation configuration language, SCL for short. This is the language of 61850 that defines the configuration of the devices in an XML language. So you can define in XML the power system relationship between the objects that the devices are controlling, as well as defining which power system functions are assigned to which device, and how those devices are configured for those power system functions. And very important too is it does allow support for private extensions. So this allows people to use SCL to carry proprietary information in a file so that if a device needs something proprietary, you can still get that information to the device via an SCL file. There's 4 basic types of SCL files. I'm only putting the basic types here. You have the system specification description, which is a file that describes multiple substations. You've got a substation configuration description, which is the subset of that for a single substation. You've got a configured IED, which is a subset of the substation configuration description. So that's the extracted file out of an SCD is just the configured IEDs. And then there's an IED capability description, an ICD file. This is produced by the developer that tells you what the device is capable of. The only requirement in 61850 is that any device that passes conformance test has to have an ICD file for it. So the way this works together is you have an SSD file. It's the entire system. You have one or more substations. Each of the substations has one or more configured IED description files contained within it. So this gives you a nice, easy way to exchange information about the power system itself, as well as how the devices are configured within that power system. And so if we look at the relationship of what's the difference between an IED capability description and a configured IED description, essentially you have the ICD files, what the IED is capable of. So an IED might be capable of having 16 current transformer cards plugged into it. But in fact, in your application, you only use 2. So in this particular case, you would have 16 of the VTL, I can't remember the logical node designation, but versus the CID file would only have 2 of them in it. Plus, the CID file contains the substation-specific configuration information. So, for instance, the settings, the configuration parameters associated with that specific device will be contained in that file. We looked at this naming of this prefix, and a lot of the prefix naming is derived from the SCL file. This is a rather, a little bit obtuse one, but here you're looking at voltages, voltage levels, bay designations, and IED designations that are using 2-character names here. And when you import an SCL file to a device, these designations get carried in and will create for instance, a connection ID that's associated with the station bus number, the voltage levels, the bay numbers, the device, and the access points. Here's an XCBR prefix here would be E1, Q1, QA1 would be the prefix that would be used on a circuit breaker designation to define that that circuit breaker is in a particular position within the power system. These designations here are just illustrative. They could be anything, and basically are going to be based on whatever standards you guys implement in your systems and what the tooling is capable of performing. I'm not going to go through this in too much detail here, but there is there's a SCL file that defines this information in XML. This is just a very brief little header here. I can I think I got enough time just to bring this up here and just walk you through a quickie. Let's see if that comes up. Yeah, here we go. I hate going through too much XML here, but just to give you a general idea, you have the communication addressing information here under the subnetwork. You've got the services that the device supports. Here's reports settings. For instance, in this particular case, we've got dynamic data sets where the report ID is dynamic and configured by the device. We have 20 report control blocks. Here's an access point. The access point has, let's get down here. There we go. Here we got a data set definition. Right here, where you got to look at a data set that includes a status point and a quality and a measurement and a status value. Here's some measurements with amps, frequency, and voltage. There's a goose control block. Here's a report control block, which called, the name of it is unbuff mesh, and so on. This is a CID file because now we've got initialization of parameters in some of these, in this object here, so you can see some of the parameters being initialized. As we get farther on down here, now we see the logical node templates. Here's the GGIO block, which has got mode, behavior, health, a nameplate, and then one single status point, and so on. So basically, this is the file that some devices, either the tools generate for the configuration of it, or the device can read in to configure itself based on the SCL file.